Start with the edge of our solar system. Past the orbit of Neptune lies a freezing expanse stretching for billions of miles. For decades, astronomers mapped this region as a void. These extreme trans-Neptunian objects orbit far beyond Neptune. Instead of scattering, their paths cluster together toward one side of the Sun. The prevailing explanation is that a massive, unseen entity, Planet 9, uses its gravitational pull to corral these icy bodies into this tight formation. The models for this gravitational shepherding are mathematically consistent across separate simulations. Because the logic holds up, Planet 9 has become the accepted architectural rule for how we understand the mechanics of the deep outer solar system. To test that rulebook, a team of astronomers began scouring decades of survey data, specifically looking through archived images taken by instruments like the Victor M. Blanco telescope in Chile. Identifying distant worlds in archival data presents a significant challenge. The telescope images were taken months or years apart, creating sparse snapshots rather than a continuous track. The researchers built a custom algorithm designed to sift through these disconnected photographic plates. It searched for faint points of light near the sensor's limits and calculated whether they could be the same moving object, bridging the gaps across years of empty space. The algorithm identified an object spanning 19 different exposures over 7 years. They designated it 2017 OF201. Based on the amount of light it reflects, they calculate its diameter to be 700 kilometers, making it a likely dwarf planet. This diagram shows the red orbital path of this newly discovered dwarf planet. It takes 25,000 years to complete a trip around the Sun. Notice its orientation. It points in the wrong direction, cutting sharply across the established cluster of extreme trans-Neptunian objects. The existence of a dwarf planet moving entirely independent of that cluster presents a direct physical contradiction to the gravitational models that rely on Planet 9. Multi-band photometry reveals that 2017 OF201 has a dark red-tinted surface. This coloration indicates a thick layer of complex organics formed as billions of years of cosmic radiation baked the simple ices on its exterior. This model illustrates the scale of the dwarf planet's path. At its closest approach, it grazes Pluto's orbit, but at its farthest point, it travels 1,600 astronomical units, plunging deep into the inner Oort cloud, a vast spherical shell of icy debris. An object measuring 700 kilometers across cannot naturally form in the sparse reaches of the Oort cloud. The material isn't dense enough. To be here, 2017 OF201 had to form closer to the Sun before being violently ejected outward by the gravitational kick of a giant planet. Once it was thrown out that far, it encountered the galactic tide. This is the collective gravitational pull of the Milky Way galaxy itself. This external force tugged on the dwarf planet at its farthest point, warping its orbit and lifting its closest approach safely away from the giant planets that originally banished it. Decoupled from the inner solar system, 2017 OF201 has remained on this isolated track. Its current path serves as an undisturbed record, preserving the mechanics of the gravitational chaos that dominated the early solar system. That isolated track creates a unique testing ground. Researchers can now mathematically evaluate if the orbit of this new dwarf planet and the gravitational pull of the hypothesized Planet 9 can physically coexist. To find out, astronomers ran n-body dynamical simulations. These computational models calculate the gravitational interactions between multiple celestial bodies over millions of years to test the long-term stability of an orbit. When Planet 9 is added to the simulation, its gravity directly interferes, causing 2017 OF201's trajectory to wildly fluctuate. Within 100 million years, this influence would completely snap the trajectory and eject the dwarf planet from the solar system entirely. We know 2017 OF201 has been orbiting stably for billions of years. Because this object is observable on its present path, the specific version of Planet 9 used to explain outer solar system clustering likely cannot exist. This discovery forces astronomers to look beyond a single object and evaluate the statistical probability that we manage to find this dwarf planet at all. This diagram illustrates the detection problem. 2017 OF201 spends 99% of its 25,000-year orbit too far out in the dark to be seen by Earth's telescopes. It is only detectable during the fraction of its orbit when it swings closest to the Sun. If we caught one object here, probability dictates it's not an anomaly. There must be hundreds of similar bodies traversing the invisible sections. When you calculate the combined mass of hundreds of 700-kilometer-wide dwarf planets, the total is equivalent to roughly 1% of Earth's mass. This implies a significant amount of material is hiding entirely out of sight in the inner Oort cloud. To confirm the physical properties of this population, astronomers will point the Hubble Space Telescope at 2017 OF201 in 2026. They will search for orbiting moons, which will allow them to calculate the exact mass and density of the dwarf planet itself. 2017 OF201 reveals that the inner Oort cloud contains hundreds of large, icy bodies. Our maps of the outer solar system now include a population of icy worlds totaling 1% of Earth's mass, material previously hidden by distance.